morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are talking about implicit differentiation. Yes, we are going to differentiate implicitly, so let's get to it, shall we? Okay, we'll get back to the cure at the end of the video. Before we get going with implicit differentiation, I want to take a look at the chain rule, and perhaps you haven't seen it presented this way. Probably you have thought of the chain rule as the derivative of the outside function multiplied by the derivative of the inside function, which is true, but we're going to talk about it a bit more formally. So let's consider we have a function f of x equal to the square root of x, and then another function g of x equals x squared plus 1. And then we're going to talk about the composite f of g of x, and we're going to let that be equal to, or represent that with capital F of x. Well, f of g of x is equal to the square root of x squared plus 1, because we replace the x with the x squared plus 1 here. And I'm just going to rewrite it as x squared plus 1 to the 1/2 power, because we're about to differentiate it. So if I take the derivative of cap f of x, well, the derivative of the outside would be the derivative of the composite function times the derivative of the inside part times g of x, okay? And so you differentiate that as normal, and you end up with 1/2 times x squared plus 1 to the negative 1/2 times 2x using the chain rule. All done, okay? Well, another way, or a more formal way to look at it, is to, of course, start with cap f of x equals root x squared plus 1. And we're going to use some substitution. We're going to let u equal the inside function g of x, which is x squared plus 1. So now, all of a sudden, cap f of x is equal to the square root of u, which I'll again rewrite as u to the 1/2. So the derivative of cap f of x is now equal to the derivative of y with respect to u, because our y, which is cap f of x, is in terms of u, times the derivative of the inside function u with respect to x. And the reason why it's du dx is we have defined u as being equal to x squared plus 1. So it's the derivative of u with respect to x, okay? So if we do that, dy du, u to the 1/2, the derivative is 1/2 u to the negative 1/2. Du dx is the derivative of x squared plus 1, or 2x. And then we're done with the derivative, the mechanics of it. So we substitute x squared plus 1 back in for u, and we end up with the exact same thing that we got here, okay? Now, do you have to think of it like this every single time? No, but it is the formal definition, and it is what drives the engine of implicit differentiation. And it's summed up here. Dy dx equals dy du times du dx if we let y equal the inside function, and u equals f of x, the outside function. Why do we need this? Why do we need to be able to differentiate implicitly? Well, sometimes we cannot solve for y by hand. For example, right here, we can't solve this for y, but we might be interested in its derivative. We can do that if we have an implicit relationship between y and x. We can solve for dy dx, and we do that by applying the chain, product, quotient, and any other rules as appropriate. We will always apply the chain rule. That's, again, that's what drives the bus here. A more specific example is why, just so you can see why we would need it. If I have the equation x cubed plus y cubed equals 6xy, that is a famous curve, the folium of Descartes, and that's it right here. Now, this curve, generated by x cubed plus y cubed equals 6xy, is not a function. It fails the vertical line test. Oops, sorry about the mess, as you saw there. But it can be broken up into a piecewise function, f of x. So if you took all of these parts, here, here, and here, and put them together, you would get this curve. And individually, all of these are functions. So we replace y with this f of x, this piecewise function, which allows us to differentiate implicitly. Okay, so let's go ahead and find dy dx of x squared plus y squared equals 25, which is the equation of a circle with center 0, 0 and radius of 5. And the reason we're going to use implicit differentiation is we cannot solve directly for x. So just to be clear, if we tried to solve for y in terms of x, we would have y squared equals 25 minus x squared, and we get two solutions for y, which is plus or minus the square root of 25 minus x squared. So there's two parts for y, and both of them together don't form a function. So we're going to use implicit differentiation. So the way we do that is we take the derivative of both sides of the equation. So d dx of x squared plus y squared is equal to d dx of 25. So d dx, so that's the derivative with respect to x of x squared plus the derivative with respect to x of y squared is equal to 0, because the derivative of a constant is 0. So here's our issue, and I'll work that a little bit up here. D dx of y squared is equal to, using the chain rule, d dy of y squared times dy dx, derivative of outside times derivative of the inside, because y, we can think of y as in terms of x. And so that would equal the derivative d dy of y squared is simply 2y dy dx. And so this is going to end up to be what we're solving for, dy dx. So d dx of x squared is 2x. d dx of y squared is equal to 2y dy dx, which is equal to 0 still. Solving for dy dx, we're going to subtract 2x from both sides, so we would have 2y dy dx is equal to negative 2x, and let me go up here, divide both sides by 2y, and I get dy dx is equal to negative x over y. So this is dy dx of x squared plus y squared equals 25, and we are in two variables, which is fine. Let me show you why and how it can be useful by solving part B. Find an equation of the tangent to the circle, x squared plus y squared equals 25 at the point 3, 4. So we're going to find an equation of the tangent. Okay. So to find an equation, we need a point and the slope. So let's do the slope first. The slope is found by using the derivative. So the slope is simply going to be negative x over y. And if it's at this point, these are my coordinates, that's negative 3/4. Okay. And let me just show you real quick what we're talking about here. I have the circle, or I graph the circle by graphing both points of the both parts of the function, positive root 25 minus x squared and negative root 25 minus x squared right here. And let me move that over a bit so you can see. Okay, so I have the circle. I graphed a tangent line to the circle with a random point, and this is the equation of the tangent line. Now, we are interested in the tangent at the point 3, 4. So let me change that to a 3. So now the tangent is at 3, 4, and notice the slope is negative 0.75, which is exactly what we found right here, negative 3/4. And so now we'll do the equation of the line, y minus the tangent line, y minus y1 equals m times x minus x1. So we have the slope, negative 3/4, and we need a point on the line. Well, that's here. It's on the circle, and it's the point of tangency, so it's on the tangent line. So I get y minus 4 equals negative 3/4 times x minus 3. So that would be y is equal to negative 3/4 x. So that's going to be plus 9/4, and if I add 4 to that, that's 16/4, so that's going to be 25/4, which I believe is 6.25. Let's go back to our calculator. Bam, there we go. That's the equation of the tangent line. Okay, so using dy dx can be a little bit cumbersome, so we don't have to do that. We can use other symbols. I just wanted to show you quite formally how to do implicit differentiation, but we can do it much quicker. So if I have find dy dx of x squared plus y cubed equals 8. So without even writing it, if I take the derivative of both sides of this equation, so the derivative of both sides, I'll go ahead and write it out this first time, d dx of x squared plus y cubed equals d dx of 8. Well, this is going to be 2x, and d dx of y cubed is going to be 3y squared dy dx, but let's just write that as y primed, which is equal to 0. Let me just go back here and show you that's the same as 2y dy dx. I had y squared, the derivative with respect to y of y squared is 2y times dy dx. Well, we can just write that as y primed. And then to find dy dx, I'm solving for it, which I've written as y primed. That's fine. So y prime would equal negative 2y over, oops, negative 2x. Sorry about that. I hope I said x. Negative 2x over 3y squared. And we're good. We can work with that. All right, so now let's look at example B, which is a little bit more complicated. But I am not going to put the d dx in front of everything because I want you to be able to do it as quickly and efficiently as possible. But we know that's really what is behind what's happening. So we are going to take the derivative of both sides, and the derivative of x is 1 plus, and I'm going to skip this middle term just for a second, and the derivative with respect to x of y cubed becomes 3y squared dy, or y prime. Okay, that's the chain rule in action. Now here we have the product rule, uv. So that's going to be the derivative of the first, which is 2x. The derivative of x squared is 2x, times the second term, plus the first term, x squared, times the derivative of the second term. So the derivative with respect to y of y is simply 1 times y prime. Okay, now I'm going to redo this and not write the 1. I'm just going to put y prime, just like we put y prime here. Plus, and of course the derivative of 100 is 0. So now I need to solve for y prime. So I'm going to gather my y primes on one side, x squared y prime plus 3y squared y prime would be equal to negative 1 minus 2xy. And factor out a y prime, and we get x squared plus 3y squared equals negative 1 minus 2xy. Divide both sides by x squared plus 3y squared, and we get y prime is equal to negative 1 minus 2xy over x squared plus 3y squared. And we're in business. And again, y prime is dy dx. Same thing. All right. Lastly, we're going to find the gradient of the tangent to this curve at the point where x equals 2. So taking the derivative of both sides, and you'll get very good at this. This will be 2x plus 3y squared y prime is equal to 0, derivative of 5. So now I need to solve for y primed. We just did this one before, didn't we? 3y squared y prime equals negative 2x. So y prime equals negative 2x over 3y squared. All right, so now I need to find the gradient or the slope. And they give me x, but they don't give me y. Well, the gradient of the tangent is on this curve. That's the whole reason we're doing it. So if I know x, I can solve for y by substituting in here. 2 squared, oops, sorry about that, plus y cubed is equal to 5. So y cubed is going to be equal to 5 minus 4, or 1. So y is equal to 1. So that means that y prime is going to be equal to negative 2 times 2, this value of x, over 3 times 1 squared, which is 3. And so your final answer is negative 4/3. So the gradient to the tangent of x squared plus y cubed equals 5 at the point where x equals 2 is negative 4/3. All right, that is all I have for today. Hope you enjoyed it. I know I did. And with that, I am out.